we're going to look at the normal distribution. I'm hoping you did this last year a little bit, but if not, that's okay because we're going to go basics. So, the normal distribution is one of the most important probability distributions in statistics. Many naturally occurring phenomena have a distribution that is normal or approximately normal. Some examples are physical attributes of a population, such as height, weight, and arm length, the mass of each fruit from an orchard, scores for tests taken by a large proportion. Once a normal model has been established, we can use it to make predictions about a population and to answer other relevant questions. I like this one because this is essentially all the exam stuff for SACE, but yeah, basically nearly anything with lots and lots of factors ends up being normally distributed. So, how a normal distribution arises. So, consider a taxi driver who records the distance he travels each day. The distance he travels will vary due to several factors. For example, the number of passengers he collects, the speed limits on the routes he takes, the amount of traffic on the roads, the number of hours he works. The distance travelled most days will be close to the mean, while on fewer days he will travel much longer or much shorter distances. This results in a bell-shaped distribution for the distance travelled, and this distribution is symmetric about the mean. So basically there's lots of factors in regards to this example that affects how far the taxi drives. So because there's so many factors, that's why it ends up being a normal distribution. So the normal probability density function. So if x is normally distributed, then its probability density function is this. Now we're not going to worry about it too much. But the reason this is the probability density function is if you integrate that, it's going to give you 1 between, obviously, negative infinity and infinity. So, one thing we do need to remember if you're not too sure, mu is the mean, and sigma squared is the variance of the distribution, and the graph of this function is called the normal curve. We also write with this notation. So you'll see over here that this squiggly line is red, is distributed as. So basically it's saying x is distributed as a normal distribution. That's what the n means. And in the brackets you'll have the mean. So say the mean was 8 and say the variance was 4. That's what you'd have it as n, 8, 4. From there you could obviously then find the standard deviation. So the standard deviation would be the square root of that. But we'll get into all of that down the track. So the normal curve is symmetrical about the vertical line x equals mu, which is the mean. F of x is greater than 0 for all x and is asymptotic to the x-axis. So remember, for a probability density function, that was one of the conditions. It had to be greater than 0 the whole time, so we can tick that. And since the total probability must be 1, as I said before, if we integrate that horrible function that we saw on the last slide, you'd actually get 1. So more scores are distributed closer to the mean than further away, and this results in the typical bell-shaped curve, which obviously you can see is bell-shaped. Not sure why they say it's bell-shaped. I suppose because a bell looks like that. Never really thought about it, but that would be why. This I wanted just to go through quickly just because I think it's really cool, and hopefully it'll help you to understand, I suppose, where statistics and calculus kind of fit together. So if we were to differentiate this function, and we're not going to do it, but if you did, you'd get this. If you wanted to find when that was equal to 0, you'd find that it is only equal to 0 when x is equal to mu, and this corresponds to the point on the graph when f of x is a maximum. So obviously where the maximum is the mean, and obviously because you've got a stationary point, that did not touch like it should have, we know that f dash of x is equal to that point. If we differentiate it again, we get this even more complicated function. And if you were to solve for when f double dash x is equal to 0, you'll end up getting that x is equal to the mean, or mu, plus or minus sigma, which is the standard deviation. So then you can see that the points of inflection are at mu plus sigma, which is here, and corresponds to that point on the graph, and x is mu minus sigma, which corresponds to this point on the graph. So you can actually see that obviously when you found the first derivative was equal to 0, that corresponds to the mean. And when you found the point of inflection, that's actually going to correspond to the standard deviation, or one standard deviation, away from the mean. So for a normal curve, the standard deviation is uniquely determined as the horizontal distance from the line of symmetry x equals mu, or the mean, to the point of inflection. And that's how this, I suppose, the standard deviation sort of came about. Now this slide is super important, guys. Make sure you've got this written in your book, or maybe even start your cheat sheet now and make sure this is on your cheat sheet, because you need to remember these percentages. So for a normal distribution with mean mu and standard deviation sigma, the percentage breakdown of where the random variable could lie is shown below. So approximately 68.26% of values lie between mu minus sigma and mu plus sigma, which is all three here. So as you can see here, you've got 34.13. If you times that by 2, because there's 2 of them, or if you add 34.13, I should say, if you add them together, you end up with this 68.26. Then if we go further out, so if we look at the 95.44, which lies between mu minus 2 sigma and mu plus 2 sigma, you'll add these 13.59 to, or you'll add all of these 4 together, and I can tell you right now it ends up becoming 95.44. And the final one that we look at, which is when your 3 standard deviations either side of the mean, where you're going to add this 2.15 in as well, you're going to get the 99.74%. And then I think even if you go further, oh no, the rest of it, sorry, I should say, the 0.13, because if you add that to 99.74, you add the 0.13, you're going to get 99.87, I believe. Then if you add the next one, you're going to end up with 100%. And that's with those little tail bits, which are further than the third standard deviation. So that's how obviously you can get your 100% under the bell curve, but you're going to need to remember those percentages. Okay, so here's an example where these percentages that you just wrote down in your book are going to come in handy. So the chest measurements of an 18-year-old male the chest measurements of 18-year-old male footballers are normally just distributed with a mean of 95 centimeters and a standard deviation of 8 centimeters. Find the percentage of footballers with chest measurements between 95 and 103. Now, what I expect in all of these questions throughout the statistics topic is for you to sketch every scenario, and to do that, because when you do, it makes it a lot less likely that you'll make a mistake. So we know that the mean in this case is 95 centimeters. We also know that the standard deviation, and I'm actually not going to write that there because I'm not going to be able to fit everything in, 95. We also know the mean is 8. So if we were to take 8 away, we'd end up at 88. And if we were to, nope, that's 7. Terrible maths. 87. And if we were to add 8, we'd end up at 103. Now we're looking at between 95 and 103. So we're looking between this section. So we colour that in. And we know from the slide before that that's 34.13%. And that's what you need to do in this question. But there could be questions like this in your exam, there could be questions like this in your tests, and I do expect to see those sketches. Now, what does part B say? B says, from a group of 200 18-year-old male footballers, how many would you expect to have a chest measurement between 87 and 111? So now we need to go, okay, well, if we go another 8 up from 103, we're going to get, what's that, 111. So realistically, I should still draw another scenario. That's terribly drawn. We know that we're going to have 95, 87, 103, and 111. Now obviously yours will probably be drawn maybe a bit better, but they're just sketches. So we know it's going to be all in this section. Now we know that that was 34.13, 34.13, and 13.59. Now if we add those all together, and trust me here, we get approximately 81.85% of the 218-year-old male footballers would have a chest measurement between 87 and 111. However, we haven't quite finished the question, because it says it's not asking for a percentage. It says from a group of 200, how many? So we want to know how many. So we obviously then need to use this number. I'm just going to do it up here. So we go 81.85%. The easiest way to actually do this question would be to turn that into a decimal. So 0.8185 times by 200. And that's going to give us, now I want to check the actual decimalised answer here. Give me a second. Alright, so when I did it, I got 163.7. Now we can't have 0.7 of a person. In this case, I'd round up because we're just looking at how many would you expect to have. Obviously, with this at 7, I'd round up. So I'd say approximately 164 of the male footballers should have chest sizes. And it is good practice to actually write a sentence after, so we might do this. So I'd say 164 male footballers are expected to have chest measurements good if I could fit everything in. Chest measurements between 87 centimetres and 111 centimetres. Now I should have probably done something as well up for question A. It's really good practice to try and get yourself writing a sentence about every question you're doing in statistics. There's a lot more writing to it, so just good practice. So make sure you're kind of answering the question with a sentence at the end. Alrighty, so last part is find the value of K such that approximately 16% of chest measurements are below K. So if we do our little diagram again, now again, hopefully you've written everything down, but I know for a fact here that that's 13.59%, that there is 2.15%, and the last one was 0.13%, I believe. Now if we added them together, so when I quickly did that, I got 15.87%. Now luckily in the question it says approximately 16, and if we remember originally we had 95 here, minus 8 gave us 87. So the value for K in this case is 87. So K, oh wow, I don't know what happened there. But K would be equal to, one thing you could do, you could just say K is equal to 87. And if we want to put it in a sentence, so find the value of K such that approximately 16% of chest measurements. So we could say that 16% of chest measurements are below 87 centimetres, and I should have started that off with approx 16%. Done.